Hey class, it's Jamie Batch, your instructor for A&P 2. We are continuing with chapter 19, which is all about the cardiac cycle, cardiac physiology. A little bit of heart anatomy was thrown in there also. Don't mind my terrible hair today. I just had to throw it up. It just wasn't working for me today. This chapter is chock full of physiology, so it's very intense. But if you find your niche in how you study and how you learn, this stuff makes so much sense. It's like when you finally understand it, you're like, oh, it's one of those things that's intuitive. Once you've learned the vocabulary and learned the terms, it all makes sense together. So your first job is to master the vocabulary. And then your second job is to pull all that vocabulary together. So switch to screen share mode here. Where's my little... where's my PowerPoint? Maybe it's this one. There we go. So I got to do this because I want to see the big picture, which means I got to start at the beginning of the PowerPoint, which is kind of annoying, but kind of gives us a quick review of everything that we've gone through already in this chapter. This chapter was intense. I'm glad that we, at least in this semester that I'm currently teaching, we were able to divide it up into a few weeks. Can't always do that depending on the schedule, but we went through all this, the cardiac cycle, the lub and the dub, and now we're talking about cardiac output. This is cool, and if you're a math person, you'll like it because it's kind of like mathy and formula-y, and if you're not a math person, it's okay because it's really basic. So cardiac output, or CO as it's abbreviated, this is literally defined by the amount of blood that's pumped out of the left ventricle every single minute. So there are two factors that are going to determine your cardiac output. Your heart rate is determined by beats per minute, and what we call your stroke volume. The stroke volume is the actual amount of blood that's being pumped out of that left ventricle within a given heartbeat. So it's that volume that's being pumped out. So your cardiac output is how much blood is being pumped out every minute. And we're really only focusing on the left ventricle when we talk about these terms. So heart rate and stroke volume determine cardiac output. Makes sense. If we're measuring how much blood we pump out per minute, we need to know how many times we beat and how much we beat out. That sounds weird. So it's calculated CO equals HR, heart rate, times stroke volume. That's the tricky math for you. It's really not tricky. So your body can actually adjust our cardiac output. How? How could we change our cardiac output? Well, if we change our heart rate or we change our stroke volume, right? Any changes in those two factors are going to change our cardiac output. If you increase your heart rate, if you increase your stroke volume, well, you're going to increase your cardiac output. If you increase one and decrease the other, right, you're going to have an effect on your overall cardiac output. So just to kind of put some numbers here, if your heart rate is 75 beats per minute, it's about the average, right? And your stroke volume is about 80 milliliters per beat, again, about average, then your cardiac output is 6,000 milliliters per minute. Kind of cool. Right? So this all begins with our conducting system. So in order to understand heartbeat, we have to understand how that heartbeat initiates, right? We already understand the heart sounds, but where does the heart get the instructions for that heartbeat? It's from the conducting system. So the conducting system is a group of specialized heart muscle cells or cardiocytes that are designed to basically control the rest of the heart. They're initiating and distributing that impulse that comes from the nervous system. They can do it on their own. They don't necessarily need any neural or hormonal stimulation. That's that automaticity to it. It's kind of like you set a rocking chair going, and it's just going to keep rocking for a while. That's exactly how your heartbeat works. It's your brain isn't telling your heartbeat to beat every single second, but what your brain can do is tell your heartbeat to increase or decrease depending on what else is going on in the body. So, and same thing with hormones. Hormones can increase or decrease your heart rate depending on what's going on in the body. It's this whole control mechanism thing. But for the most part, your heart is just that rocking chair. Just keeps rocking. Right, automaticity. So this conducting system starts with the SA node, or the sinoatrial node. It's in the back wall of the right atrium, kind of at the top, and it's also known as our pacemaker. So this is where that pace or that kind of rhythm is initiated from. And it's then distributed to all of the other components through internodal pathways. These internodal, sorry, I'm covering up, my feet are really cold. The internodal pathways are little, they're little pathways of cells, conducting system cells, that are there to just distribute that information all the way down into the ventricles. It takes it to, first, the AV node. So you have your SA node, which is in the top corner of the right atrium, and then you have your AV node. Your AV node is right kind of in the middle of your atrium ventricles, right in that little intersection there, in that like interventricular septum. This is where your pacemaker cells are as well. So if your SA node's damaged, your heart rate can still be maintained because you have an AV node. So it's kind of a backup plan, as well as like a little helper. So this can conduct impulses pretty quickly, and it can stimulate higher impulses by stimulation of like drugs and things like that. Then we have your AV bundle or bundle branches. These are within that interventricular septum. They're normally the only electrical connection between our atria and ventricles. And then the bundle branches are sending that signal out towards the apex and out down through the ventricles. Finally, Purkinje fibers. These are large diameter conducting cells. They act like myelinated axons, and these are going to trigger, these are the cells that actually trigger the ventricular contraction. So when we look at the entire group of this conducting system, you have your SA node. Your SA node conducts through internodal pathways to the AV node. Your AV node will conduct through the AV bundle and bundle branches all the way down to the Purkinje fibers. The moderator band is a special cluster of conducting cells in the right ventricle that's just there to, again, monitor the conducting system. Basically, it's kind of like an overseer. It doesn't increase or decrease. It just is like a feedback mechanism. So here's the whole thing. So you have your action potentials that's generated by the SA node. How does that action potential get initiated? From automaticity, right? That rocking chair just keeps on going, unless it's stimulated by neural or hormonal control, right? You get a little fight or flight response, you get a little sympathetic activation, well then your SA node's going to be stimulated more. Or you're resting and digesting, so your SA node's going to be, kind of slowed down a little bit and inhibited. Or your vagus nerve, that's the one that controls your heart. Like that could either back off and increase your heart rate, or increase to decrease your heart rate, because vagus is parasympathetic. So either way, that impulse from the SA node is going to travel through those internodal pathways down through the atria. Look what's happening in the heart. Once the atria are depolarized, boom, we have atrial systole. Right? Our atrias are contracting, our AV valves are open, etc. Then our atria relax. Our AV valves are closing as our AV node is stimulated, and all of the impulses are traveling down through the AV bundle and the bundle branches to the Purkinje fibers, and finally our ventricles can contract after they are fully depolarized. And then the whole thing happens again. So you can pause the video here, go back and review the conducting system. Let's talk about how different cardiac muscle cells are from skeletal muscles for a minute. So skeletal muscles are, that action potential is very brief. You get that twitch contraction that can be created. It's very short, right? And that's where the sarcoplasmic reticulum, or SR, are taking up the calcium very quickly, so the refractory periods are very short. Twitches can actually cause summation. You can get tetanus, right? This buildup of tension that can occur in skeletal muscles because that calcium can be taken up very, very quickly. So that's what is going on in the skeletal muscle. You have your action potential or your impulse, and then the contraction. in our cardiac muscle, our action potential is long. So the calcium ions are entering the cell over a longer period of time. So the contraction is a longer time, which means the refractory period actually continues into a relaxation period. So the tetanus cannot occur. The tetanic contractions cannot occur. That's how our heart muscle does not undergo wave summation or TREP or any of those kind of differing contractions that skeletal muscles can have. Our cardiac muscles don't have that because our calcium ions kind of are delayed and very slow to move in and out. That makes our refractory period very long. So the other thing that does is it means, let me back up. Something to keep in mind is that when the heart is contracting, just like when your skeletal muscles were contracting, it's not like every single cell is contracting every single time, right? Remember when your skeletal muscle is contracting, there was different muscle bundles that were being stimulated, right? Different groups, right? All through that kind of motor end plate, right? All the different motor units were being recruited at different times. Same idea here. Different cardiocytes are contracting at different times. So with first heartbeat, you might have, all of these guys contracting. With your second heartbeat, you have all of these guys contracting. So you have different cardiocytes that are contracting at each time. It's not the same ones contracting over and over again. So take a look at this. The action potential, again, very slow. That calcium lingers, which means our contraction is much longer. So there are three main stages of our action potential in our cardiocytes. You have that rapid depolarization. Depolarization is always rapid. It's exactly the same as with our skeletal muscle fibers. You get to threshold, sodium channels open, sodium rushes into the cell. They're called fast sodium channels because they open really quickly, and they only remain open for a few milliseconds. So it's basically like, get in as soon as you can. Then you have this plateau phase. This is where the membrane potential remains near zero, and you have these opposing factors that maintain it. You have your fast sodium channels and your slow calcium channels. So the fast sodium channels are going to close as you approach that positive 30 millivolts, and the cell begins pumping that sodium back out. And then your slow calcium channels are going to remain open, allowing for calcium to rush into the cell. So the calcium keeps rushing in. They remain open for a fairly long period of time. The third phase is our repolarization. The calcium channels close, our potassium channels open, so potassium goes out, and the net result is rapid depolarization, getting us back to our resting membrane potential so that our cell can then be repolarized or depolarized again. So here's that plateau phase. This plateau phase is where those calcium ions are remaining in the cell, right? They're not leaving just yet. And that allows for that absolute refractory period to be very, very long compared to a skeletal muscle, right? The relative refractory period is very short, and that's when they can be stimulated again without having any adverse effects. So you can pause the video here, go back and review this little section. We're going to keep going, talking about the autonomic effects on the heart rate. So you have what's called a pacemaker potential. The pacemaker cells that are within the sinoatrial node or SA node and the AV node, they cannot maintain a stable resting potential. In fact, after repolarization, the membranes are going to gradually drift towards the threshold, and that gradual depolarization is called a prepotential or a pacemaker potential. So this pacemaker potential naturally happens, and it's basically a result of this spontaneous depolarization. The SA nodes cells do this super fast, and that establishes the heart rate. Notice the heart rate that the SA node is generating is around 80 to 100 beats per minute. Right? Most of us have a resting heart rate lower than that. So the impulse from the SA node goes down to the AV node. The AV node cells, they can do it on their own, but they also take the instructions from the SA node. So this is our normal resting heart rate and this pre-potential happens naturally. So as soon as that depolarization happens, they're going to kind of get ready to go again, and then the SA node takes over. So that pre-potential is kind of like prepping for the actual depolarization. So our heart is actually under parasympathetic influence. Any factors that change the rate of the depolarization most of the time is parasympathetic. The parasympathetic stimulation on our heart is typically acetylcholine from the parasympathetic neurons, right? Like the vagus nerve, for instance, opens the calcium channels, and that's going to slow the rate of depolarization by kind of hyperpolarizing those cells. It extends the duration of that repolarization and ultimately slows the heart rate. So ACH is going to slow the heart rate, which is kind of different than in other parts of our body where acetylcholine is enhancing contraction, right? In our skeletal muscles, that's what acetylcholine does, right? Acetylcholine is the kind of influence over our skeletal muscles, whereas here it acts in a parasympathetic way by slowing things down. So that it brings about that hyperpolarization by allowing more potassium into the cell. Anytime you have more potassium in the cell, you get that hyperpolarization, which means it's harder for that cell to reach threshold and get to an action potential. Sympathetic influence on our heart is going to be caused by epinephrine or norepinephrine. It's going to bind to beta-1 receptors, lead to the opening of ion channels, increasing the rate of depolarization. It also shortens the repolarization phase, which then increases the heart rate, kind of keeps it moving. There's sympathetic stimulation. Notice that our repolarization does not go all the way down to -60. It's much shorter because that refractory period is shorter. With resting heart rate, obviously it's going to vary with age, general health, how physically fit you are, etc. Normal 60 to 100 beats per minute. Bradycardia is anything less than 60 beats per minute. Tachycardia is anything above 100 beats per minute. Most of us fell in that normal range. There are different areas of our brain that control those. Sorry, I lost my train of thought. There are different areas of our brain that control our heart rate or that contraction cycle, right? This is all coming from the conducting cycle. So you have a cardioacceleratory center in the medulla oblongata, in the MO. Just kind of looking back at my notes because I had a whole bunch of stuff. Your book switches things up on me from how I normally teach things. But that's okay. With our cardioacceleratory center, that's obviously going to increase our heart rate. Sympathetic innervation is going to have control over this. Those fibers are innervating the conducting system, the nodes, AV nodes, the ventricular myocardium. They're all going to be basically stimulated by the cardioacceleratory center in the medulla oblongata. So what happens in general, that's why I was looking back at my notes, because normally this is all in order in my notes, but for some reason your book threw me for a little loop. That's okay. So typically what happens is you'll have a like a stimulus, like high carbon dioxide level or low oxygen level, right? Maybe you just increased your movement, right? And you just started to go for a fast walk, or you just started jogging, right? Well, all of that's going to be detected in your medulla oblongata, where these centers are, where there's a small break in the blood-brain barrier, so the medulla oblongata can kind of test for the chemoreceptors, and the baroreceptors can kind of check blood pressure and carbon dioxide levels. If it detects they're off, then that cardioacceleratory center can be inhibited or activated. And if it's activated, it's going to cause this sympathetic activation in our heart. It's going to cause that increased heart rate, saying, whoa, we have increased pressure going on, or we have decreased pressure, or we have increased carbon dioxide, so we need to increase the heart rate so we can get that carbon dioxide out. Otherwise, we're going to have too much acid in our blood, et cetera, et cetera. The cardioinhibitory center does the exact opposite. It's also located in the medulla oblongata. So this is controlling our parasympathetic neurons to all in all decrease our heart rate. The parasympathetic activation comes through the vagus nerve, goes in through the cardiac plexus, innervates the nodes and the atrial musculature. Normally, the resting heart rate is slower than the actual heart rate that's being driven by the SA node, and that's because parasympathetic stimulation dominates. So in other words, remember, our SA node is generating action potentials at 80 to 100 beats per minute, but our heart rates are typically lower than that. And that's because our heart is constantly being slowed down by our cardioinhibitory center, by this parasympathetic activation. So our SA node wants to be hyper and give us lots of heartbeats, but the brakes are put on. Why does our heart do that instead of our heart naturally being slower and then having to get sped up? Well, think about it. When you're driving a car, right? Say you're driving a car downhill, right? You're driving a car downhill and you have your brakes on. If you take your brake off, you don't have to do anything to get it to go faster, right? You take your brake off and it's automatically going to go faster just because of momentum. Same thing with your heart, right? You have that brake on all the time, that parasympathetic activation on all the time, but that SA node's telling it to go faster, just naturally. So as soon as you take that brake off, your heart is automatically going to go faster without any extra work. So instead of your sympathetic kind of always being on, and then you have to slow it down, right? It takes longer to slow something down than if it already has that inertia from that SA node making it go fast. So our normal resting heart rate is typically lower than what the SA node impulses dictate. And that's because of that cardioinhibitory center. So here you have just an overall picture of where these bundles are and how they're getting into the heart. Sympathetic coming in through the ganglion, pre- and post-ganglionic fibers through the cardiac nerve, parasympathetic coming down through the vagus nerve. And you can pause the video here, go back and review this section on the conducting system. Actually, I think I'm going to stop the video here because the next section goes into a whole different topic that I will cover in a different video just because it kind of makes sense to do it that way. I'll see you next time. Bye.